Okay, we are recording. Thank you everybody for joining us today from the comfort of your computers, especially on like a rainy, cool day like this. Please give Marty your full attention while he talks about his mine methane project.
Okay, thanks much, Liz, and appreciate folks coming out this afternoon and having to listen to about the lurid topic of mine methane emissions from underground coal mines. It's not lost on me that it's a Friday, it's St. Patrick's Day, and there are actually two NCAA tournament games going on as we speak. In that vein, I'll try to be efficient and interesting for you today and hopefully make it worth your time. Before kind of getting into the topic for the day, I want to acknowledge my collaborators on this effort. Our own Steve Greb and Cortland Ebel helped out on this project a great deal. We also worked with Marcella Guzman out of UK Chemistry, and then Sean Bailey out of UK Engineering and the UAV lab that he heads up. So just to be sure, before I get any further along here, does everyone see the screen okay?
Yep.
Okay, good. Okay, so so let me just kind of give you a high-level overview before we get into some of the science. So back kind of coming out of our COVID days in 2021, an idea was hatched in the Energy and Environment Cabinet to analyze methane emissions from underground coal mines. There was an idea that perhaps, maybe these emissions could be monetized, either by directly capturing the methane and or by getting carbon credits that could then be sold on the carbon markets. I'm really not going to speak to those questions today directly, but if we want to have a conversation later, I'm happy to do that. But in reality, what this project ended up doing, and actually I think ended up making an important contribution to the effort in looking at methane emissions from coal mines, is that we starting off with a review of the Mine Safety and Health Administration and the EPA greenhouse gas reporting program data for the last decade. We developed a research program to analyze methane emissions from 22 underground mines in eastern and western Kentucky. The analysis were done on basically infrared spectrometers that were deployed on KGS vehicles, an airplane, and a drone. And then at the end of the day, and I'll speak to this a bit more, we really kind of evaluated the effectiveness of these different measurement platforms and recognizing and assessing methane emissions. So before, just as a kind of a preamble for this and the next one or two slides, let me give you a motivation for doing this kind of work. As you know, methane is a main component of natural gas. It's a relatively clean source of energy, with relatively being the operative word there. With that said, since the mid-1750s, methane leakage primarily from anthropogenic sources is responsible for about 25 to almost 33% of radiative forcing that we've seen in the atmosphere. And despite the fact that it's present in the atmosphere at significantly lower concentrations as compared to CO2. So for example, I checked yesterday, global methane concentrations are just shy of 1.9 parts per million, whereas CO2 is, I think the last time I checked was 420 and counting. Despite this difference, methane really has an outsized impact, and I kind of show this graphically on the right side here, where if you look at it over a 20-year period, the global warming potential of a single molecule of methane is equivalent to about 84 molecules of CO2. For that reason, at least in the near term, it's of considerable concern in trying to mitigate near-term global warming. And you can see the quote by Emery Lovins at the top from the Rocky Mountain Institute, who makes the astute observation that, ignoring methane while focusing on CO2 is like trying to work on a chronic illness all the while you're bleeding out in some major artery. So one of the challenge really kind of getting at abating methane emissions is that there are just so many sources of methane. It's really pervasive throughout all facets of our life, and that includes agriculture, of course, the energy sector with oil and gas, and the coal sector. It's also comes from natural sources such as wetlands and peat bogs and things like that. So this particular map was done, was actually developed in 2015 and 14 and published in 2016 by Massakers and others, where they did the painstaking work of actually aggregating methane sources throughout the U.S. And you can see the methane concentrations, basically their emissions per annum, per kilometer squared here, with the hot colors representing higher emissions, and of course the cooler colors lower emissions. Again, there's thousands of sources coming from all sectors. And the challenge, of course, is if you're doing discrete and ground-based measurements, you're basically climbing a hill that never relents because you're always going to be behind the curve and trying to get ahead of, get a handle on emissions. So one way to get at this challenge that I mentioned in the previous slide about trying to do discrete measurements, say on a ground-based campaign, is to actually do remote measurements that are either done from satellites or aircraft or some combination. And so this particular plot attempts to try to translate that that strategy, where you have a kind of a sampling program or campaign, and in the temporal scale of that campaign going from seconds all the way up to years along the x-axis. And then the spatial scale of that analysis, you're looking at individual sources at the lower end of the y-axis, or are you in a position, depending on your methods, where you can look more regionally at broader sources. And so if you kind of look along this spectrum here of greater time scales and then greater length scales, kind of at this at the lower left here, you're looking at discrete measurements, either done on foot or by vehicle, and then moving up and to the right, you then start moving into the realm where you're doing remote measurements, either from NA covariance towers, aircraft, and then finally probably the current state of understanding and technology, we now have the ability to examine methane emissions from satellites, and depending on the orbits, those satellites then can revisit sites multiple times over. And the only thing that's required then is that you have a client or someone that's willing to pay the cost to actually turn that spectrometer on and then process that data once it's acquired. Just to kind of give you a sense for the scale of the problem in the U.S. alone, if we just look at gas transport pipelines, you're looking at well in excess of 3,000 miles of pipelines. And so those types of very large scales really do require that we have and do our best to try to use remote measurements as much as possible. So I'll use this location slide to really kind of be our first salvo into the work that was done as part of this project. So as I mentioned, we, through a screening process, identified 22 underground mines, both in the eastern and western side of the state. And this map, this two maps shows the distribution of these mines. In western Kentucky, we identified 3 active mines, 2 non-productive active, and 2 abandoned. So these categories are categories that are recognized by the Mine Safety and Health Administration. And so They're fairly self-explanatory. Non-productive active is a mine that's temporarily shuttered. My understanding is that there's some hope that maybe given improvement in product prices or something going forward, those mines that are classified as non-productive active might eventually revert to becoming an active mine again. So what you can see is that on the western side of the state, we have fewer mines, but the mines tend to be larger over there, and we'll see that in a subsequent plot. Whereas in the eastern side of the state, the mines are more numerous, but they tend to be smaller. So as we go through this, I'm not going to, because of the time considerations, I'm only going to grab a few of these mines as examples to demonstrate what I think are some of the important points that we discovered as part of this project. Okay, so the first step in our process, as I mentioned, was kind of a screening of the EPA databases and the MSHA databases. And this particular plot shows quarterly coal production along the x-axis versus then methane emissions in metric tons on the y-axis. Okay. I show information here from 7 mines in eastern and western Kentucky. The eastern Kentucky mines are shown with the icons that are filled, whereas the western Kentucky mines are shown with the icons that are open. So I only show 7 mines because this is data that I have in which I have both methane emissions and coal production available for these mines. This data goes from 2016 into about 2020, depending on the activity of the mine. So the interesting thing is when if you go back a decade, which is where I get my first data from the EPA in 2011, there were 24 mines in Kentucky that reported to the EPA and were required to do so. So that reporting threshold is 25,000 metric tons of CO2 equivalent per year. By the time we get 5 years later, by the time we get to 2016, the number of mines reporting in has dropped from 24 to 7. Okay. And then even though I don't show it, by the time we come into 2020, we're now down to 4 mines in the state that meet the EPA reporting thresholds. So 2 things are happening here. First off, the number of operating mines in the state is decreasing, okay? And contrary to some current advertisements on TV, this decline in the number of mines and the amount of coal that's being mined actually was happening well before we got our current president. So, so this has kind of been a long-term trend, and it's continued regardless of politics. It's being driven by macroeconomic factors, and that primarily the rise of natural gas that's displacing coal. And then specific to Kentucky has also been the depletion of resource. Okay, so we've been at this for well over 100 years, and coal is a finite resource. So, those are the factors that are at play. So the thing that I would point out to you here is that kind of in general, as the amount of coal that's being mined increases, we then see a commensurate increase with the amount of methane that's emitted. But as you can see, it's not a very clean relationship. There's a lot of noise, and it's especially noisy in my mind, especially for mines in eastern Kentucky, where the amount of methane, even for a given mine and for a given amount of coal, can vary quite a bit. So Steve and Cortland may want to speak to that a little bit more as we kind of wrap up today, but kind of what that tells me is that depending on the coal that's being mined and the coal face, that can then impact the amount of methane that's being liberated. So I guess the other thing I want to point out to you here is as the number of large emitters decreases, in the state. That means that we still have smaller mines that are operated. And keep in mind that these mines are not required to report to EPA. So therefore, really the amount of methane that we're reporting for the state from the underground coal mine sector is probably significantly underreported. So back up here. So in addition to looking at the overall mines and using this as a selection process, our idea, our strategy was to select both very large mines and very small mines, because we feel like that reflects kind of the state of play, so to speak, of coal mining in Kentucky. But the other thing it does from an analytical perspective is that it then puts our instruments that we try to use for detection at looking at a variety of potential emissions magnitudes. So kind of at the upper right, you're going to have these really large magnitude emissions we'd expect to be successful here. But then when you get down to these lower levels of emissions, the question then becomes, do you really have that analytical threshold in a real field setting to detect methane? So in addition to selecting mines, for each of the mines, we selected specific parts of the mine that could emit methane. So this particular example is from the number 77 mine in Perry County, okay? It's a Google Earth image, and for each mine, we identified several infrastructure features that could be emitters. So the most likely and the most prominent emitter for any coal mine is actually the exhaust fan. So here at the bottom part of this image, you can see the number 77 fan. So that's the exhaust fan that's exhausting the ventilation air that they're using to ventilate the mine. So potential secondary sources of methane could also include the belt portal. So in other words, that's the area where the belts are actually coming out from underground with the coal and then bringing that to the surface and then transferring that then to a pile of coal where that's then offloaded onto trucks or trains or whatever for transport to coal-fired generation plants. So we did this for each of the 22 mines. We identified these various features and provided the lat long data, not only for our own use, but also for the aircraft surveys. So what I'd like to do here is just kind of spend a couple of minutes looking at this graphic to kind of give us a groundwork for understanding the measurements from the aircraft perspective as we go forward. So in general, incoming solar radiation from the sun comes to us in the form of UV and visible light, right? So it's an incoming solar radiation, and that impacts the ground, which then re-emits the radiation out to space, largely in the infrared spectrum. So this is an ongoing process. And then in the atmosphere, we have greenhouse gases that include CO2, water vapor, methane, and then actually a host of other, let's see what happened here. I lost my screen. You still with me there? So we have a collection of other greenhouse gases that absorb this outgoing infrared radiation and then re-emit some of that infrared radiation back to the surface. And that is the so-called greenhouse gas effect. And it turns out that methane is absorbed in the infrared radiation, absorbs infrared radiation in the 1600 to 1700 nanometer spectrum, part of the infrared spectrum, and this is basically the shortwave infrared part of the electromagnetic spectrum. So we can use that relationship then exploit that relationship to understand basically how much methane or other greenhouse gas there is in the atmosphere. And again, that amount of absorbance is proportional to the concentration of the gas in the atmosphere, okay? So the way aircraft or satellite measurements are done is that over a certain column height, so they have and we'll see this in the next slide, they have a spectrometer on board, and they can then measure the amount of infrared radiation that makes it into that spectrometer. And of course, as the amount of methane or some other greenhouse gas increases, the amount of infrared radiation that's received in the spectrometer is reduced because it's been absorbed. And with calibration, we can then make a measurement then on the amount of that particular gas. And it turns out that these gases have unique wavelengths at which they absorb. And so that allows us then to isolate like the absorption wavelength for methane versus CO2, say, versus water vapor, okay? So you can kind of do this for kind of a global atmospheric average because methane is well mixed over a relatively short time span. But then what happens then is through anthropogenic activities, that background concentration of methane or some other greenhouse gas, say CO2, then gets perturbed by the introduction from anthropogenic sources. So I kind of show this graphically at the lower right. You know, we can imagine this might be a stack, say, from a coal-fired plant, or it could be a ventilation fan that's emitting, we'll say for our purposes, methane. That methane then in the lower atmosphere is aloft and gets dispersed by the wind. And then if you have an aircraft that flies over that source, basically the anthropogenic source has increased the concentration of methane. And so the amount of absorption that occurs in that column of air that's being absorbed by the aircraft is increased. And that then shows up in the spectrometer measurement in the aircraft. So it turns out that for our purposes, this column height of air is about 3,000 meters from the spectrometer to the ground. So this is actually looking in the fuselage of the GHGSat aircraft. So a little background. So when we started this project, the idea was that we would actually maybe try to use satellite data to look at methane emissions. And the same principles that I just described with the aircraft apply in the case of the satellite, except that the satellite, I think, is at 300 kilometers above the Earth's surface, so considerably higher up. And but as a result of that greater altitude, it does not have the detection threshold nor the spatial resolution that you might get in an aircraft. And it actually costs quite a bit more, not surprisingly. So when we sat down with this company, GHGSat, which is a Canadian company, to discuss our strategies, they suggested an aircraft. So a little bit of background on GHGSat, and I can answer any additional questions people might have later. So GHGSat is a Canadian company. They launched their first methane detecting satellite probably about 5 or 6 years ago, called IRIS. Okay, so they were early players in the game. And so they're basically a for-profit company. And what they do is they contract with private entities, in our case, basically a university and state agency. They contract with them to fly methane measurement campaigns. And what they do in these kind of cases, you basically are paying, of course, they provide you some kind of estimate on the cost to fly a certain number of what they call assets. And then you develop a measurement campaign with them. And so, as I said, in our case, we opted because of the better spatial resolution and higher detection thresholds, we opted to do an aircraft survey. They based this particular aircraft, which is a Piper Navajo, out of Bowling Green. So that allowed them to access the mines in Eastern Kentucky and then also mines in Western Kentucky from one central location. So the aircraft is basically two people in the aircraft during a campaign. There's the spectrometer operator and then the pilot. Okay. And so there's a portal in the belly of the aircraft. There is a camera, this so-called Fabi-Perot wide-angle fixed cavity camera and spectrometer that's focused downward, that then measures the amount of infrared radiation that comes back in toward the belly of the plane. The remarkable thing about all this is on a gimbal assembly, so that camera stays pretty level even during conditions that may be pretty choppy in terms of flying the aircraft. The aircraft flies at about, as I said, about 3,000 meter altitude and at about 120 knots. Under those conditions, the investigation swath on the ground is about 750 meters. There's a remarkable spatial resolution of about 0.75 meters squared. And the detection threshold is also pretty remarkable at about 100 parts per billion fresh methane. So this map comes from a report supplied to us from GHGSAP. And as I said, we provided them with 22 underground mines. At the end of the day, they ended up surveying 21 mines over the time period. Actually, that's wrong. That's November 12th through November 19th, 2021. So a little over a 1 week period. They flew each of these 21 mines at least twice and on separate days. And then actually some mines were surveyed 3 or 4 times depending on the flight paths. So this is a map. I appreciate that this is hard to see and I apologize. This is a Google Earth map that was provided to us by GHGSAP. But the take home point here is that these really, the red linear tracks represent the flight path that GHGSAP took between our mine assets when the spectrometer was running. So basically they're trying to maximize and be most efficient in their flight times when they fly these paths. So what I'm going to do here in the next few slides is just show you a couple examples of some responses that GHGSAT picked up as they flew these. So what I'm going to do here, I'm going to try to do this without, I'm going to just show you real quick here. See if I can, I'm going to pull you into a Google Earth image that allows us to see some of the attributes a little bit quicker. So this is the Pride Mine. This is a Google Earth image of the Pride Mine in Muhlenberg County. So I'm going to pull out here. And so what you can see here, just to orient you, for those of you who are familiar, there's the Western Kentucky Parkway. And then here's the mine road coming in. And so you can see the targets that we provided to GHGSAT to cover on this, right? So they basically, their flight path took them across these 4 particular infrastructure targets. And the reason actually for pulling this in is I want to show you how accurately we can identify the infrastructure. And so that's actually the ventilation fan for the Pride Mine. I'll circle back to that. So I would just say, keep that mental image in your eye as we go forward. Sorry. I ended up back at my beginning. Find my cursor here. Okay, sorry about that. So there's that, here's that fan, that ventilation fan we were just looking at. And so here's an image that's higher up, okay? And the square that's on the right side is this area that's enlarged here. So on the right-hand side, that's the fan that I pointed out previously, okay? And what you see here is this colored plume going off to the upper right. And what that plume shows is actually methane concentrations that are above background at hundreds of ppb. So the scale bar here in the center represents, you know, going from the bottom 150 up to 500 ppb above background. So hotter colors represent methane concentrations that are higher concentrations of methane above background. And then cooler colors, of course, are lower concentrations above background. So what we can see here is that we see this plume trailing off to the upper right or to the northeast. And that jibes on that particular day. This was done on November 16th. That jibes with a predominantly southwest wind on that day. So the one thing that GHGSat does is that given this plume distribution and the concentrations that are observed within it, they are able then to use that in local atmospheric conditions, wind speed and direction, to use an inverse model to estimate the emission rate of methane coming off of that fan. And in this particular example, it's 132 kilograms per hour, but the error associated with that is pretty significant at 78 kilograms per hour. And I can talk to folks more about this later, about this inverse modeling, if they're interested. But as you can see, it's subject to a lot of error. So here's the mine, the same mine 3 days later. And I show you this because you can see on the time scale of days, there can be quite a bit of variation in what that plume looks like. So again, it's the same set of images we saw in the previous slide. Scale bar is the same with the concentrations of methane above background. And again, now instead we see a very small plume trailing off more to the west-northwest, which jibes with kind of a predominant southeast wind on that day. So I'll circle back and make some comments about the aircraft campaign here as we get toward the end of my presentation. So what I'd like to do next is actually spend this in the next few slides talking about the aircraft, the vehicle-based measurements. So what I did was I took a KGS vehicle. So this is actually, I guess, our forerunner. And I have, we have a spectrometer at KGS, a Lycor spectrometer, and then Marcelo Guzman supplied a second spectrometer that, like the aircraft spectrometer, measured the amount of methane that's being absorbed in the infrared spectrum. Now, unlike the aircraft, the spectrometers that I have on the KGS vehicles actually have pumps on them that actually actively pull air into an optical cavity where the methane's measured. So these PTFE tubes that you see running out the side window are connected to the roof rack. And so those are basically intakes where methane is brought into the infrared spectrometers, okay? So this is all powered with a deep cell marine battery, powers the spectrometers. In addition to spectrometers, I always brought along a Kestrel weather station so I could see what was going on with wind speed and direction and atmospheric pressure. And then there was a Bueller GPS pod that was mounted on the window here so that I was tracking lat longs as the vehicle was doing surveys looking at methane emissions. So a couple important points is that one of the spectrometers measured methane, ethane, and water vapor, whereas another one measured methane, CO2, and water vapor. So we got a nice coverage of different greenhouse gases using the two spectrometers. So one of the things that I want to emphasize here is when we started this program, and this is a big deal, we contacted, I think, almost all the mining companies to get permission to come onto property to do measurements closer to the ventilation fans. And without exception, we were either ignored or were told, thanks, but no thanks. Okay. So the result of that is that, at least in the case of the vehicle surveys, we were largely relegated to doing what I call fence line surveys. So basically, we're on the outside looking in. And so in order to look at methane emissions off of these different infrastructure elements of the mines, we basically had to find mines in which the roads were in somewhat close proximity to those mine infrastructure elements. And you'll see that strategy here in the next slide. Okay. So this is an example of the Cardinal Mine in Hopkins County. Okay. And so there's a lot of interesting things going on here, and I'll step you through it as we unpack it. Okay. So this is Highway 41, which runs along the south side of the Cardinal Mine. And it turns out that adjacent to the mine, there's actually a TC Energy gas compression station, which adds a further wrinkle on our effort to look at methane emissions. Okay. So what I did when I collected the spectrometer data and the methane data, I basically tied that distribution of that data to the GPS lat long data using the similar timestamps. So that allowed me then to plot methane concentrations in space in Google Earth. Okay. So what we're looking at here is a driving survey that I did along Withers Road, then heading east along Highway Alternate 41, and then back up James Ellis Road. And the red pins represent methane concentrations that were recorded by the vehicle as it made this fence line survey around the Cardinal Mine, and then also this TC gas compression station. So basically, these are methane concentrations above background, since GHGSat recorded values on what we call a delta basis. These values represent delta values. So so the stuff here with the lower amplitude pins are pretty much background values. But then what happens is you see the pins really go off scale here. So we're getting to values, that are basically, it goes, you can't see it right here, but they're 10 to 15 times above background. So basically values like 30 parts per million methane. So that's where these pins appear to be floating up in the air because the concentrations are so high. So as I continue around the traverse and then head north up James Ellis Road, we'll see it better in the next slide. We get another anomaly. So we actually end up with two methane anomalies in this area. So there's a second parameter that's plotted here, and that's actually shown with the blue pins. And I think I'll try to illustrate that more in the next slide. Now, so here's an enlargement of that previous slide. So we discussed, the red pins represent the magnitude of methane emissions above background. The blue pins actually represent the ratio of methane to ethane. Okay. So remember, we were recording ethane concentrations at the same time. And going back to that previous slide, we can see that values here, this methane ratio stays fairly constant. And then when we get into this area where we get the really high methane concentrations, look what happens to the methane-ethane ratio. It drops off. And then as we come out of the anomaly, it comes back to background. And then we come north on James Ellis Road. And notice here that even though we have a methane anomaly, there's no change in the methane-ethane ratio. So what's going on here is we have methane that's being generated, and anthropogenic methane is being generated, but it's really coming from two sources. And those two sources really have geochemically distinct fingerprints. The methane that's coming off of leakage off this TC Energy station is related to natural gas, okay? And natural gas tends to have higher molecular weight hydrocarbons associated with it, including ethane, propane, and so forth. As a result of that, the methane-ethane ratio drops, whereas in contrast, the methane anomaly that's coming off the Cardinal Fan mine, which is right here, there's no change in the methane-ethane ratio. So we can see that it is geochemically distinct from the methane that's being generated from the natural gas infrastructure. So this was a really interesting and cool discovery that even in areas where you have active mining, there's potentially other sources of methane, and you have to be careful not to go to a default mode of attributing those methane sources to the coal mines. So in addition to active mines, I looked at some of the inactive mines in the state. And so here's an example of the Dotiki mine, which is now abandoned over in Webster County. At one point, it was one of the largest mines in the state. The fan was located over on the kind of on this right side or the east side of the map. Again, driving survey, as I previously described, with the red pins representing methane concentrations above background. And we can see this nice little anomaly that occurs right here. At the time, I attributed that anomaly to methane that was still coming off the belt portal. So basically kind of a latent methane that's being generated. Yeah, I later just came across new information that suggested that maybe that is not the source of the methane, but maybe it's actually coming from some other part of the coal mine. And I'm happy to talk to folks about that later if need be. So I'm going to kind of violate one of the central tenets of giving a presentation by throwing a real ugly table up here, but I think it really does an effective job of kind of showing how well the airplane and the vehicle campaigns perform in terms of detecting anomalous methane with the various mines. So just in summary, without really kind of getting into the weeds on the table, so this upper group of mines are active mines. This middle group of mines are these so-called non-productive active mines. And then finally, this lower set of 4 mines are the abandoned mines. And they're generally arranged from increasing coal production at the top to less coal production here at the bottom, and of course, zero coal production for the non-productive active and abandoned mines. On the left column where you see the red and green, okay, this basically shows where yes, I got a detect, so that's shown with green, or no, I did not get a detect, shown with red. So this first column are the airplane anomalies, okay? So you can see by and large, the airplane-based survey was only effective at resolving anomalies at 3 of the 21 mines they flew. By contrast, where I was able to get close to some of the underground mines with the vehicle, we were able to resolve anomalies at 7 out of 10 active mines, and then 2 out of 5 inactive mines. So I have to tell you that these results are actually reversed of what I would have anticipated at the beginning of the project. And the reason for that is that given the really high detection thresholds that are being reported by GHGSat, and the fact that they're flying directly over the top of these sources, I would have expected them to be in a much better position to resolve these anomalies, as opposed to being in a vehicle where you may not get close enough to resolve an anomaly, and then you're also subject more to the whims of local topography, and then also the wind direction and speed. So this came as a bit of a surprise. And I will tell you, I'm attempting to write this up for publication. But it is always a more interesting challenge to write up a journal publication in which you're reporting by and large negative results, and trying to speculate on why those results are negative as opposed to positive results. But I think it's important that we get that out there, because I do think it's important for the scientific community, given all the press and notoriety that aircraft and satellite measurements are getting, that they understand there are some potential limitations. So this is just kind of restating some of the things that I've already discussed. So I don't really want to get, you don't really need to bury into these at all, so you can kind of see this for yourself. So I guess what I'd like to do here, let's see, how am I doing here? So 45 minutes. So last 5 minutes, let's talk about drones, okay? So at the end of the day, drones, you know, they were going to be really kind of an important component of this project. But when we were denied access to the mine sites, the ability to actually deploy a drone became much more challenged, because the bottom line is that roads that are close to mines often have a lot of power lines. There's a lot of tree growth and so on and so forth. And so deploying the drones in a manner that's safe, legal, and close enough to the mine infrastructure to actually resolve something can be quite a challenge. So at the end of the day, we actually only had 2 mines that met kind of the criteria for safety, and then also for our analytical purposes and feeling like we had a chance to actually resolve any anomalies. So I worked with the mining, the mechanical engineering group, Sean Bailey's group. They have a UAV laboratory. And for our purposes, we used, and for you guys that are, gals that are drone weenies, there's information there for you to mull over. So a DJI S1000 octocopter. It's equipped with sensors for pressure, temperature, relative humidity, and wind speed direction. And then out on the arms of the octocopter are 4 anemometers that record wind speed and direction. That data is then backed out to track basically the direction and of the drone once it's aloft. So what I'd like to do here is show you a couple of videos from the Straight Creek mine in Bell County. And then I'll show you kind of some of what those results look like. So the first video I'll play is a fan. This is the exhaust fan at Straight Creek mine. And just to give you a sense, so this fan is oriented horizontally, okay? So this. So this road, and again, coming back to the road access, as you can see, it's really in a nice position with respect to the fan to have a chance to look at more closely at emissions coming off the fan. And so the next video, so the engineering UAV van is parked right just before this bridge, right? And before this grove of trees, they're parked here. And we'll look at the drone as it's deployed for survey. Okay, so as you can see, we basically use the clearing of the trees along the trace of the road to do a series of north-south traverses, looking at methane concentrations. Oh, sorry. Let's go to the next one. Yeah, so here's that road that we were looking at, looking to the north. Here's the fan located here at the upper part of the diagram. And in this particular case, I plotted the methane concentrations above background that were observed by the drone as it's flying about 20 to 25 meters above the ground surface. Okay, so we see 2 anomalies coming off the fan here, right? And then this is finally what that looks like in profile. So the black curve shows the altitude of the drone. This is one of the traverses. We actually flew, I think we ended up with 10 traverses back and forth. So I'm just showing one of the traverses. So this is as it's, as it's ascending, comes to altitude, and then we then stabilized. Like I said, that's about 22 meters above the ground surface. And then the blue curve actually shows then methane concentrations above background. So we can see that we get that peak that we saw in the previous image, and then the second methane peak. So if we go back, we have this peak, the initial peak here, and then there's a second methane peak here, right here. So the interesting thing about this is like an interesting learning experience is that on subsequent trips by the drone, basically along the same route, these peaks soon disappeared. And it's not clear to me the reason for that, because the spectrometer on the drone is deployed, the tubes for the intakes are deployed actually above the level of the rotor wash. So we're trying to avoid having rotor wash impact our ability to do measurements. So yeah, it's not clear to me what's going on, but if indeed, we lose that methane concentration pretty rapidly going up and it dissipates, that could suggest an impact the ability of something like an aircraft then to pick up methane anomalies. So yeah, that's what I have to say for today. And I'm happy to answer any questions that folks might have. And thanks for your time. I appreciate it. Are you with me, Liz? Yes.
Yeah, I'm here.
Okay.
And thank you. That was great. So yeah, if anybody has any questions.
Marty?
Yeah.
Pete Edstein here. Did you think about doing anything with a cavity ring down that's tuned for methane? Would there be any value in looking at isotopes within the methane that would be specific to different sources?
Yeah, I mean, that certainly, I took discrete samples, Pete, and sent them into a lab. But yeah, I mean, if you had a cavity ring down spectrometer with isotope capabilities on location, yeah, I mean, that would be an important important way to maybe look at some of the differences in methane. The interesting thing is Pete, is that actually at the Straight Creek mine that I just showed you, I was sufficiently confident that the methane there was coming from the coal mine that I did go ahead and collect samples actually on the same day that we flew the drone survey. And it turns out, isotopically and molecularly speaking, it looks like a mature thermogenic gas that's derived from oil and gas, with the primary exception being that it is not accompanied by the higher molecular weight hydrocarbons. So it's a straight up methane with a del C13 value of about -46 per mil. Yeah, about -42 per mil, I should say. And but it doesn't have, like I said, it's a pretty dry gas. It's just straight up methane.
Thanks, Pete. Any other questions for anybody? Okay. Well, thank you, Marty.
Yeah.
That was really great. That was really interesting.
So yeah, I appreciate your time and your interest.
Everybody have a good weekend.
Yep.
Go UK. Yes, go UK.